Hello everyone. This one is our second video on the application of a PDE. So in this video, you are going to learn about two applications, one-dimensional heat flow and the two-dimensional heat flow. So let me understand first here what is one-dimensional heat flow. In one-dimensional heat flow, we have a bar which have a very negligible thickness. So you'll observe it is a finite bar that were taken. So this is the rod that we have. Okay, this rod. So in this rod, which is a finite rod, that means the length of the rod is from x equal to 0, x is equal to 0 to x is equal to L. So we have, this is the L and this is a 0 here. So 0 to L, that is L is the length. In wave equation, we said u of xt we have, and that u of xt represents the position of the string at a distance x and a time t. Here we have exactly same u of xt is again here, but x represents the distance again, and t represents t represents a time. So at a distance x and at a time t, u represents now a temperature. That is only the change. In wave equation, u is a position of the string at that location at a distance x. Here u is a temperature. U is a temperature at a distance x and a time t. So that is our aim. Our aim is to find out the temperature in the rod at any point, say x. So suppose this distance is x only, this length is x, and for that x here is suppose that fx. Okay, so that is some temperature we have, we are given. So the first important thing, generally we have again a boundary conditions and initial condition. Here boundary condition is exactly similar to the wave equation. So both the boundaries at x equal to 0, x equal to 0 and x equal to L, the temperature is a 0. So you will observe u of 0t is a 0, u of lt is a 0. So this is exactly same conditions that we have in wave equation. Wave equation, in vibration of string, we seen both the ends are fixed, so there is a zero displacement there. And here both the ends are insulated. Okay, both the ends are insulated, so the temperature at both the ends are 0. So u is a 0. So you can say u of xt, or you can say t of x comma t. Both way you can write it, whatever the way, but u or t, they are temperature function. So these temperatures are 0 at a distance x. At this distance x, we are given some initial temperature fx. You'll observe the third condition is initial condition. U of x0 means at t equal to 0, we are given some fx, and that f of x is the initial temperature. Okay, there is initial displacement in wave equation. Here we have initial temperature. That is initial conditions. Only three conditions are there in one-dimensional heat flow, and our aim is to find out the general temperature at any distance x and at any time t, uh, for that heat flow. So heat is flowing through that rod. So somewhere there is a temperature is given. So in this case, temperature is given at this location, and that temperature is given at a distance x, and that initial temperature is given with an equation f of x. We have that function, and then we can calculate the temperature at any point. Now come to the differential equation. The differential equation, this is the differential equation of one-dimensional heat flow. Remember, in the differential equation of one-dimensional heat flow, we have dou u by dou t is equal to c square dou 2u by dou x square, and the wave equation we have dou 2u by dou t square is equal to you can take c square on any side, so you can adjust that. C square dou 2u by dou t square is equal to dou 2u by dou x square, something like this. So in wave equation, both the derivatives are of second order with respect to t, time t, and with respect to displacement. But in a heat equation, we have the first order derivative with respect to time. So that is the identification of wave and heat equation. So this is the wave equation, and here is a heat equation. So the general solution with the general solution of the one-dimensional heat flow is given as, always it is given in the form C1 cos mx plus C2 sin mx into e raised to minus c square m square t. There are again three arbitrary constants, say C1, C2, and the third is m. So this m is appeared at three places. So our aim is to find out C1, C2, and m, these three constant, by using the boundary conditions and one initial condition. And that is the aim of one-dimensional heat flow. Okay, so in every example near about, we have to do the similar calculations in this application. So just like you seen in the wave equation, always you have to apply one boundary condition, then you have okay, so you have to apply that one by one, and you will get, at the end you will require Fourier series. Exactly same thing is here also. So come to the solution now. The solution, the question is here. The question that we are given is on the screen. We are given one equation. Now you will observe, in original equation we have c square, and because of c square we have here e raised to minus c square m square t. Original equation, if there is a c square dou 2u by dou x square, so whatever the coefficient of dou 2u by dou x square is there, so that c square appeared here. So in a solution we have to change that accordingly. So here coefficient of dou 2u by dou x square is k now. So the general solution u of xt will be c1 cos mx plus c2 sin mx into e raised to minus, there is c square, so here is just k, because c square is k here. In this case, that c square is k m square t. So this is the equation number one. That is the general solution of one-dimensional heat flow. Why we started one-dimensional heat flow? Because the equation, whatever equation we are given, dou u by dou t, this represents the one-dimensional heat flow equation. So we return a general solution. Now we have the conditions. So say condition number, this is the condition number 2, this is the condition number 3, and remember this condition, bounded condition, is of no use. So sometimes it is given, sometimes it not. But the important two boundary condition, condition 2 and 3, and lastly the condition 4, where you have to apply half range Fourier series. So let me apply the condition 2, 3, 4 on the equation 1, one by one. So just we say, by the equation 1 and equation 2, by 1 and 2, we have to replace x by 0. We have u of 0t, that is equation 1, u of 0t is a 0, means x is a 0 and keep t as it is. So if x is a 0, cos 0 is 1, sin 0 is a 0, so we get c1 cos 0 is 1, c2 sin 0 is 0, so only that. So e raised to minus k m square t. Now you will observe the multiplication of c1 and the multiplication of e raised to this is a 0. Obviously the second term, e raised to minus k m square t, cannot be 0 for all values of t, because t is a variable appeared in that term. So this gives us only the c1 can be a 0. The c1 can be a 0. So we got one constant here. The constant c1 we got, and we can replace in equation 1. So solution 1 becomes u of xt, u of x comma t, which is a temperature at a distance x and a time t, becomes c2 sin mx into e raised to minus k m square t, that I take as equation number 5. Now let me say by 2 and 5, let me apply the second condition, which is u of lt is also 0. Temperature at the second end, that at L, u of lt, u of L comma t is a 0. Let me replace x by L. So this is c2 sin ml e raised to minus k m square t. Exactly similar situations like the wave equation we have. Now multiplication of c2, multiplication of sin ml, and the multiplication of this term, the product of three terms is a 0. So one of the terms should be 0. You will observe e raised to minus km square t cannot be 0 for all t because the variable t appeared. C2, if you take C2 0 and if you replace that back in equation 5, our u of xt becomes 0. We get the general solution as a 0 solution, which is a trivial solution. So C2 also cannot be 0. So we left with only one thing, and that is sine ml should be 0. Sine of ml should be 0. Now sine theta is a 0, then theta is n pi. So ml should be n pi, and so m is n pi by l, n pi by l, where n takes the values 1, 2, 3, and so on. There are infinitely many values because this sine theta is a 0 for n pi, where n is an integer, where n should be integer. So solution 5 becomes, so by 5, equation 5, u of xt, u of xt is equal to, now remember that many values are there, so we take summation and varies from 1 to infinity, that's c2 sine n pi x by l into e raised to e raised to minus k n square pi square t upon l square. Okay, that way. So this is the equation 6. Equation 6, which is our general solution that will become. But now uh, uh, now one last condition is left, that is condition number 4, which is the initial temperature. This is the condition that is we have to apply. So which always gives us the half range sine series. So condition number 4 and the solution 6. So by 4 and 6, by 4 and 6, we have u of x0. U of x0 is fx, but that fx is in this case the fx is, you will observe, u0 x upon l, where u0 and l are constant. u0 x upon l, u0 x upon l, and we are going to replace t by 0 in equation 6 now. Summation n varies from 1 to infinity. Remember, t is a 0, so c2 sine n pi x by l as it is, and e raised to 0, anything raised to 0 is 1, that's 1. But what is this, which is half range, which is half range sine series, half range sine series. And because of the half range sine series, we can get the value of c2 by the formula, and that formula is, therefore c2 is 2 by l integration 0 to l fx. Fx is in this case u0 x by l sine n pi x by l dx. Remember, u0 upon l is a constant, so 2 times u0 upon l square is outside. This l into l is l square, and now this x is u, this x is u, and the remaining is v, this one, and we are applying generalized by part. The generalized by part will become u is x, v1 is integration of sine becomes minus cos n pi x upon l divided by n pi upon l minus u dash, that is 1, and integration of minus cos minus sine n pi x upon l upon n square pi square upon l square, that is a 0 to l, that is the limit. But as usual, the value of sine goes to the 0, the term of that goes to the 0. Just a minute. So because of that, uh, we are replacing the value now. We are replacing upper limit minus lower limit 2u0 upon l square, and we are replacing x by l. So this is l. When x is L, so it become cos n pi. So minus of minus 1 raised to n upon n pi by L, n pi upon L. This is for upper limit. For lower limit x is 0, that is 0 only. That's one. So this LL gets cancelled. No, not gets cancelled. This L comes in the numerator. But actually, all L gets cancelled. This L, and this L square. Everything gets cancelled there. And we left with 2u0 minus 1 raised to n plus 1 upon n pi. So that is the value we got a C2. Hence, the solution 6 will become. In 6, just we have to replace the value of C2 and that becomes a particular solution of this one-dimensional heat flow. One-dimensional heat flow. So temperature, now if initial temperature is given U0 x upon L, the temperature at any time t and at any distance x is given by the formula. Now by 6 now, by 6, and this equation I'll write on the next page here, which is a u of xt is equal to summation n varies from 1 to infinity. The value of C2 we got as a 2u0 minus 1 raised to n plus 1 upon n pi. Then we get sine n pi x upon L into e raised to minus k n square pi square t upon L square. And that is the final answer. This is the required answer for one-dimensional heat flow there. Okay, so this way you should complete the one-dimensional heat flow example. If you understood the wave equation, remember this is a more simpler than the wave equation, because in wave equation we have to remove that 4-5 constants. Here just we have to remove the 3 constant only. So it becomes a simple for one-dimensional heat flow. So there are 2 more problems that are given. Mainly the last step will change for these equations. Here's one more problem. You can go through that your own. So choice here just what I'm going to do it. I will show you one more problem, one last problem for two-dimensional heat flow. Now in two-dimensional heat flow is a third application of a partial differential equation, but that equation is also known as a Laplace equation. It is a Laplace equation. You will observe this equation is a Laplace equation because it is in the form of del square u equal to 0. This equation is del square u is a 0. Del is actually that operator. Del is like okay, I will not go in that. Del square is like dou square by dou x square plus dou square by dou y square. Because of that, del square equal to u is a Laplace equation or two-dimensional heat flow equation. So in two-dimensional heat equation, okay, if you see the first case 1, there we have now instead of rod, we have a plate. This is the plate that we have. You will observe this plate is there. So it is a two-dimensional plate. This zigzag indicates y is infinity, means it is infinite plate. So along y-axis, this plate is infinite. It is not bounded. But yes, it have 3 boundaries. First boundary is on this side. What is this? X is 0. First boundary is x is 0. Next y equal to 0 is the second boundary. And here x equal to L is third boundary. So it is bounded by 3 sides, but fourth side is not bounded. This is the rectangular plate that we have. For this rectangular plate, we are giving some initial temperature. This is Fx. Fx is the initial temperature we are given. And we have to find out u of x comma y. What is u of x comma y? U of xy is the temperature at a point xy. At any point xy, that is u of xy is the temperature. When we say y is a 0, that is u of x and y is a 0, and that is suppose Fx is given, we may say Fx is the initial temperature, Fx is the temperature. These are boundary condition only. In two-dimensional heat flow, there are only boundary condition. There is no initial condition. So how many boundaries are there? 3 boundaries. So on 3 boundaries, there should be some condition. So on one of the boundary, say y is a 0, Fx is written. means u of x0 is fx. That means on this boundary some temperature is given as fx, but on the other two boundaries that is a zero temperature, means like u of for x equal to L, that is u of x is L, Ly, u of Ly is a 0. Same thing, u of x is a 0, so u of 0y is also 0. So this boundary is kept at 0 temperature, other boundary is also kept at 0 temperature, and third boundary is kept at fx. And now we have to solve this problem. Now we have to solve the problem that dou 2u by dou x square plus dou 2u by dou y square equal to 0. So whenever there is a case 1, generally the solution selected when the plate is have the unbounded, the plate is unbounded along y direction. Suppose plate is unbounded in y direction, that is the diagram shown there, then the solution will be taken this one. This is the general solution for that. This is the general solution for that. These derivations are there in the book, and there are logic behind that, why the solution should be this one and why this only satisfy the given conditions. Because of that, the solution is derived like this. But suppose we change the position of a plate, rectangular plate, and our rectangular plate is unbounded along x-axis, unbounded along x-axis, then the solution is again interchanged. You'll observe the terms of x change to the y and terms of y are changed to the x here. So this way you have to select the solution first. And the last, third case, if the plate is bounded, this is third case. Third case, you will observe the diagram. In this diagram, this plate is bounded. This is bounded. You will observe on all the four sides it is bounded. So this is bounded plate, two-dimensional plate, and in this plate, on this plate, we have four boundaries now. We have four boundary conditions. You will observe three of the boundaries are kept at a 0 temperature. This is the first boundary which is at 0 temperature, second boundary at a 0 temperature, third boundary with, but the one of the boundary will have a non-zero temperature. At least one boundary should have non-zero temperature. Remember, if all the four boundaries have non-zero temperature, then also we can solve the problem, but that becomes too lengthy. So definitely it will not come in the exam. Only at least you should solve first of all for non-zero temperature at one boundary only, minimum, maximum one boundary, I will say. So whenever it is a bounded plate, whenever it is a bounded plate, the general solution is given by either this or this. Both are correct. Both are correct. Choice is yours. You can use any one of that, any one of that. And what is ultimate aim in all these problems? To find out a particular solution with given boundary condition and initial conditions. So in this case, only boundary conditions are there. So our aim is to find out, the value of this C1. Okay, the value of C1, then value of C2, and the value of M. C1, C2, C3, C4, and M. So total 5 constants are there. So generally this problem become again a lengthy. This problem is actually very lengthy. It is just like a wave equation or little bit more than wave equation, but exactly similar things are there. First of all, we are going to use the boundary conditions which gives us a 0 value, and at the end we'll apply non-zero temperature condition to where you can use a half range sine series again, half range sine series there, that way. But the selection of the solution is important there. Okay, so let me do one example only. So here is the Laplace equation, dou 2u by dou x square plus dou 2u by dou y square equal to 0. It is a two-dimensional heat flow equation where we are given four conditions. We are given v equal to 0 when y is infinity, v is 0 when x is a 0. So actually when y is infinity means it is unbounded. It is unbounded along y direction. It is unbounded because y is infinity. Y can take infinity value also, means which one? The case one only. This one. This one is the case only. So you can draw the diagram also if you want, and without diagram also you can continue. But you should identify which type of the plate you are given. Here y is equal to infinity. Y equal to infinity indicates just a minute. So y equal to infinity, this indicates the plate is unbounded along y direction. If it is unbounded along y direction, so what should be the solution? The solution is this first one, c1 cos mx plus c2 sin mx, c3 e raised to my plus c4 e raised to minus my. So we can start a solution as, let the temperature at any point u of x comma y is c1 cos mx plus c2 sin mx into c3 e raised to my plus c4 e raised to minus my. So that about the equation 1. This is the general solution for the plate which is unbounded along y direction. This plate is unbounded along y direction. Now you will observe when y is infinity, the temperature is zero there. So when we move away from x-axis or along y direction, then temperature is becoming zero that side. The other three conditions are there. So let me write in equation form. Let me write these boundary conditions here. Given, so here v is used. So choice is your whether you want to write u of xy or v of xy. So both are same. So if you want v of xy, you can start with the same. So let v of xy is a temperature. V of xy is a temperature at a point x comma y. Then this is a general temperature. The first condition we are given actually is v of, see, x is there. There is no condition on x, but y is infinity. V of x infinity is 0. So that is a condition 2. When y is infinity, v is 0. V of, now v is a 0 when x is a 0. When x is a 0 and there is no condition on y, so v of 0 y is also 0. That is condition 3. Actually, the second condition. Third condition, when x is 1, actually it is bounded now. For x is 1, so x is fixed and y is there. When x is 1, y, then also it is 0. And the last condition, this last condition is v of when y is a 0 and there is x, v of x0 is given as fx, which is x into 1 minus x. So this is the fifth condition. So all these 1 to 4 conditions written from 2 to 4 to 2 to 5 there. 2 to 5 there. So our aim is to use the equation 1 and apply these condition 2 to 5 one by one, so that we get the particular solution. Just check, if you replace y by infinity, e raised to minus infinity is 0 and e raised to infinity is infinity. So you cannot apply the condition 2 at the beginning. Condition 2 cannot be applied at the beginning because you replace y by infinity, c3 e raised to my becomes infinity, undefined. So that is not possible. So let me apply the condition 3, 4 first and then condition 2. We'll go one by one. So by condition 1 and by equation 1 and 3, by 1 and 3, I will say by 1 and 3. Before this, let I take some space here because later on it is difficult to add the space there. Yeah, this is already happened there. Sorry, my mistake. If I take, okay, okay. So that is enough space now to solve this problem. So we are using the condition number 3 in the equation 1. So what is condition 3? Condition 3 is v of 0y is 0. What we have to replace in then 1? We have replace x by 0. If x is a 0, see cos 0 is 1, that is c1, but sin 0 is a 0, c3 e raised to my plus c4 e raised to minus my. This only we left. Now the same thing will happen always, as usual, everywhere. What is that? Multiplication of c1 and this multiplication of the bracket is a 0. Now this bracket cannot be 0 for all values of y. So what should be then? Then this gives us c1 should be 0. c1 should be 0. So one of the constant we received. So solution 1 will become the solution 1 will become, so by 1, v of xy, v of x comma y will become, now c1 is a 0. I think we have c1 cos mx plus c2 sin mx, is it? Yeah, correct. C2 sin mx only left. C2 sin mx into c3 e raised to my plus c4 e raised to minus my. So as usual, this c2 can be merged in the bracket. So we can get inside the bracket this sin mx, this c2 c3 I am taking as a c5, e raised to my plus c2 c4 as a c6 e raised to minus my, that way. Now we have this v of xy as a general temperature, this temperature at a point xy, where what is the c5? C5 is c2 c3, and what is the c6? C6 is a c2 c4. If you want, you can write down that also, okay, if you want. So what is the next equation? 6. So this is our solution 6. Now in solution 6, how many constant left? C5, c6 and m. 3 constant we have to find out with the help of 3 remaining boundary condition. So which one we should apply now? Let me check. If we apply again, it is not possible to apply condition 1, so we should apply the condition 4 only. Condition 4 only. Why condition 1 is not applicable? Because e raised to my is still there, and when y is infinity, when y is a infinity, uh, actually yes, we can apply that. We can apply that also here also. Let me come to that condition also. Condition 1, can we go to the condition 1? V of x infinity is a 0. V of x infinity is a 0. So by 2 and by 1 and sorry, by 2 and 6, by, you can apply at beginning also. My mistake. You can apply that at the beginning also. By 2 and 6, what is that condition? V of x infinity. V of x infinity is a 0. V of x infinity is a 0. This implies, you will observe, when you replace y by infinity, v should be 0. Now you will observe e raised to the coefficient of c6. This is y is infinity, so e raised to minus infinity is a 0. So it doesn't create a problem. But when you replace y by infinity, e raised to infinity is infinity. Now this e raised to infinity, this term is a 0 provided c5 should be 0. Okay, that c5 should be 0. So this condition already tells us c5 should be 0. Now this c5 can be a 0 at because of y is infinity. So this can be, you can observe at the beginning also, you can apply that condition. So solution 6 become v of xy is, actually you can apply this condition at the beginning here only, that then also it is correct, both way it is correct. So when you apply this by 1 and 2 only, you will observe this c3 will be 0. C3 should be 0 because e raised to my is there. Okay, so that way you should say, and you will come to the similar answer here. So if c5 is a 0, the solution will become sin mx into c6 and e raised to minus my. So that is a solution 7. So this is the next solution because of that condition. Now we are going to apply the condition number 4, which is v of 1 comma y is a 0. V of 1 comma y is 0. That is a condition number 4. So by 4 and 7, by 4 and 7, what is the 4? V of 1 comma y is a 0. So we are going to replace x by 1. So we get sine 1, sine of m only, c6 e raised to minus my. Okay, now in this case you will observe the multiplication of 3 terms, sin m, c6 and e raised to minus my is a 0. Remember, C6 cannot be 0. If C6 is a 0, V of xy becomes 0. We get a trivial solution. E raised to my cannot be 0 because y variable appeared there. For each value of y cannot be 0. Sin m should be 0. So this gives us sin m. Sin of m should be 0. Sin theta is a 0 provided theta is n pi. So m is n pi. M is a n pi where n takes the value 1, 2, 3 and so on. So solution 7 become this solution 7 become. So in this 7 equation we are going to replace this solution 7 will become v of xy become a summation now and varies from 1 to infinity, that c6 constant as it is, sine of n pi x, sine n pi x into e raised to minus n pi y. That's one. That is a solution 8. Solution 8. But now last condition is left, which is the condition number 5. View of x0 is x into 1 minus x. View of x0, that is a condition 5. So by 5 and 8, by 5 and 8, view of x0 is x into 1 minus x, x into 1 minus x, which is summation n varies from 1 to infinity, c6 sine n pi x, sine n pi x. You will observe why we are replacing 0. E raised to 0 is 1, which is a half range sine series. Exactly same things are there in all the three applications. At the end you always come across half range sine series only. So the half range sine series is a prerequisite of application of a PDE, you can say. So you can mention here which is half range sine series. Therefore, the value of C6 will get by half range sine series formula. That is, C6 is a 2 by L. In this case, remember L is a 1. Why it is 1? Because x varies, x ki limit jo di hai, boundary, that is 0 to 1 we are given. So L is 1 here. So first you write the formula otherwise. So 2 by L integration 0 to L fx sine n pi x upon L dx. This is general, but L is 1. So it is a 2 integration 0 to 1 x into 1 minus x. I can write x minus x square. X into 1 minus x, this term. X into 1 minus x is written as x minus x square. They are same. This is sine n pi x only dx. Obviously, we have to use that generalized by part. The first term is a u, this one is a u, and this one is a v. By generalized by part, we can get the required value of a C6 now. So C6 will be 2 as it is. By generalized by part, u is x minus x square. V1 integration of a sine. Integration of sine is a minus cos n pi x upon n pi minus u v1 minus u dash 1 minus 2x v2 integration minus cos is a minus sine n pi x upon n square pi square plus u double dash, which is a minus 2, and now integration of this minus sign become plus cos n pi x upon n cube pi cube. So this is the generalized by part where the limits are 0 to 1. As usual, the terms of sine goes to the 0. The second term is a 0. In the first and last term, we will replace upper and lower limit, which gives us the value for C6. So C6 will become, if we replace this x by 1 in the first term, this term is a 0, so no need to replace there. But last term, yes, we should replace. So this 2 is there outside. This minus 2 cos n pi. Cos n pi is a minus 1 raised to n upon n cube pi cube. N cube pi cube. So this is for upper limit 1. For lower limit, now when we replace x by 0, then also this term is a 0. So actually, this term is a 0. This term becomes a 0 for both upper and lower limit. Both upper and lower limit. So first and second terms are 0, there is no calculation. But last term, there is a lower limit minus sign, that minus minus is a plus 2, cos 0 is 1, so upon n cube pi cube. So that's one. So we can observe that n cube pi cube can be 2 is also common. So 2 into 2 is a 4. 4 upon n cube pi cube is a common, and we're left with 1 minus minus 1 raised to n. So this is the value of C6, which we should replace in the equation 8. In the equation 8, if we replace it, we get the most general, particular solution of the two-dimensional heat flow. So V of xy, last step. Thus, equation 8 become by 8 V of xy is summation n varies from 1 to infinity. C6 means 4 upon n cube pi cube 1 minus minus 1 raised to n, sine n pi x e raised to minus n pi y. I think that is a complete particular solution. E raised to minus, yes, correct. So that about the end of your application of PD. There is a 3 application: one dimensional heat flow, two dimensional heat flow, and the wave equation. And in all the 3 we have similar methods to solve. Everywhere we have to find out the values of a constant. Everywhere at the end you have to use a half range sine series, and you get a particular solution of that differential equation. Okay, so thank you.